This is our last video in this series on application frameworks, and it will also be the shortest video. I just want to introduce you to frameworks 2 and 3, which have the same common themes of networks and interrelationships and how linear algebra is used to explore those. Framework 2 I call age and stage. So suppose you have a squirrel population. Squirrel populations are unstable, frequently either collapse or take over an entire woods. You need good models. Again, you use Markov chains. So for our purposes, squirrels only live about 5 years. There's going to be a transition diagram, and this transition diagram is going to be ages. So year 0 to 1 will go to year 1 to 2 in the next year. In other words, they're a year older, and so on and so forth. So here are our actual stages. 0 to 1, birth to 1 year old, 1 year old to 2, 2 to 3, 3 to 4, and 4 to 5. Now, they're going to not all survive from 1 year to the next, so we're going to have rates of survival. So there will be fewer 1 to 2 year olds than there are 0 to 1 because some of these unfortunately won't make it. And likewise, there'll be some die off in going from 1 year to 2 year to their 2 to 3 year, and so on and so forth. There will also be fecundities. These are rates of reproduction. Now, for our purposes, we're just going to keep a very simple model and say that only a couple of age classes will be able to reproduce. But we could have all the age classes reproduce, and that means that the 0 to 1 year old age state is replenished by the inflow of newborns produced by other squirrels in various age groups. So here is our 5-year cycle again. We're going to have variables, x1, squirrels that are from birth to 1 year. So the x1 for the 0 to 1, x2, 1 to 2, x3 from 2 to 3, so on and so forth. Next year is a transition from last year, or from this current year. So fecundities are what produces newborns. So we'll have fecundities will be F2, F3, F4, and F5 for the X2, X3, X4, and X5. So the number of offspring per squirrel will be F2 in year 2, and so the number of offspring times the total number of squirrels in year 2 gives us the total number of newborns that are produced by the 2-year-old squirrels. So the survival rates will be simple proportionalities. So S1 will be a percentage of X1 that actually makes it to be the next year, and so on and so forth. The survivals will all be less than 1. The fecundities could be larger than 1. Some animals have lots of offspring at a time. So here we have our actual diagram of survivals and fecundities. And once again, we're going to assume that we have some kind of equilibrium state. So the number at x1 will be those that came through birth from the others, and then x2 next year will be some proportion of the ones that were 1 year old last year. And we're going to assume that the squirrel population stays constant. Again, there's our equilibrium. Notice we're assuming equilibrium. In reality, real squirrel populations can change exponentially. Now, we set up Gaussian elimination. Here's a very simple example. 100 squirrels for several years in a row, and we get a model. We'll look at that later. Finally, we'll also do data representation. So each data point in a large data set can represent a state, or subsets of data points represent collections of similar states. Now edges will be strengths of association between different parts of data sets. And you can use linear algebra to determine the best graph theoretic representation of the data. In other words, the best clustering, or the parts of the data that have the most information, so on and so forth. Now, alternatively, we can't do much this semester because we won't get that far, but if we continued, data can often be images. and those can be defined to be matrices. Then you can look at things like image compression and other things applied directly to a matrix. Now there is a course, Numerical Linear Algebra, where you do these sorts of things. So we'll have Markov chains in 3 different contexts, and we'll be looking at linear combinations, before and after transitions, and equilibria. Now, linear combinations of state, we'll see later on, we'll preview, these are what are known as vector spaces. Sets that are closed under linear combinations. And again, linear combinations of objects in a vector space are also in a vector space. Now, systems of equations is not enough, but it's a good place to start. So, your homework, finish up 2.1, look at the completely worked examples in D2L, and remember, if anything else, it's good practice in using Gaussian elimination.